Right. Hi everyone, my name is Desmond, and this is the BC Personal Health Management Platform, an AI-powered healthcare navigation system built for British Columbia residents. So let me first start off with the problem. So British Columbia has over 5 million residents, many of whom struggle to navigate the healthcare system when they feel unwell. The most common question people face is, should I call 911, go to the emergency room, visit a walk-in clinic, or just rest at home? Making the wrong decision has real consequences. Going to the ER for a common cold wastes hours and clogs up emergency departments. Staying home with symptoms of a heart attack could be fatal. There's currently no accessible tool that helps BC residents make informed decisions about where to seek care based on their symptoms. So that's what our platform, PC Personal Health Platform, is aiming to solve. It uses artificial intelligence and machine learning to assess symptoms, detect life-threatening emergencies, and guide users to the right level of care, all through a simple conversational interface. So our platform will have at least 6 features. Today, I'll just focus on the core feature, the symptom assessment chatbot, which is the most technically complex. So the other features are the personal health chatbot dashboard, which helps to track your assessment history over time, the BC Facility Finder, which helps to find nearby clinics, hospital, and pharmacies, the health education library, the system analytics, which shows the population level health trend visualization, and then we will also have user authentication. Okay, so um, yeah, you heard a lot of the features I've mentioned. So all this will be actually built in the remaining sprints. The authentication system and the chatbot are fully functional as of today, and I will show you how the core engine works. Okay, right. But before I demonstrate the system assessment chatbot, I want to demonstrate the architecture behind it. So let me quickly pull up the diagram. Okay, so if you could see my diagram here, the architecture overview. So this is what actually makes our project technically interesting. It's not just calling an AI API. Okay, it's a 3-layer hybrid classification system where each layer will serve a specific purpose. Okay, so we have layer 1, okay, the OpenAI NLP layer. So when a user types their symptoms in natural language, for example, the user will say, yeah, I have chest pain and feel dizzy. So the first layer will send this to OpenAI's GPT model. GPT doesn't diagnose anything. Okay, its job is to purely extract the structured data, and then what are the symptoms, how long they've lasted, how severe are they. You will convert this messy human language into a clean JSON format that the downstream layers can process. And then we have our layer 2, the CTAS safety rules. The extracted symptoms then pass through a safety critical layer based on the Canadian Trust and Acuity Scale, the same framework used in the real Canadian emergency departments. So this layer has 14 deterministic rules that check for life-threatening patterns like cardiac symptoms, stroke signs, or seizures. If a match is found, the system immediately tells the users to call 911 or go to the ER. Okay, the ML model, you see the next layer, never even runs. This is a deliberate design decision. You never want a statistical model to be the gatekeeper for life-threatening emergencies. And only if the symptoms, okay, as you can see here, only the symptoms are not an emergency, okay, they'll pass to the machine learning layer. So this is a random forest classifier trained on 41 disease categories. It predicts what condition the symptoms might indicate and assigns an urgency level. Okay, urgent, routine, self-care. And um, you notice there's a confidence statement here, confidence more than 70%. So what is this? This is actually our key safety feature. The ML model will output a confidence score. If it's 70% or above, we trust the predictions and show the ML result. If it's below 70%, okay, no worries. We'll fall back to OpenAI for general health guidance. This is critical because the model was trained on 41 specific diseases. If someone describes symptoms for a condition outside those 41 categories, the model will be uncertain. So, and the fallback will ensure that we will still get useful advice rather than a wrong classification. So in summary, let's make it very simple. Layer 1 helps to understand, layer 2 protects, and layer 3 classifies with a safety net for uncertainty. So let me show you all of this in action now, right? Okay, so this is our login screen. So you can see in our login screen, there's a login tab and register tab. So register is basically for new users to input their personal information, and also we recommend them to input in the health profile like age, gender, BC Health Authority, their existing conditions. So all this data will be collected in the users table stored in the SQLite database, which we will make use of it to come up with some meaningful analysis for the personal health dashboards. Okay, but for today's demonstration, I just want to log in and show you guys the symptom assessment chatbot. So let's get into action. Okay, username test@test.com. Password is password 123. Okay, let's log in. All right. Okay. So we have successfully logged in. So you can see that our platform has 6 pages in the sidebar. Okay. We have home, symptom assessment, my dashboard, facility finder, health, library, system analytics. So all these other pages currently they are just placeholder pages. So I won't click into them. We'll be focusing on symptom assessment chatbot. So let us navigate into symptom assessment chatbot. All right. Okay. Okay, notice there's a medical disclaimer at the top. Important disclaimer. Okay, this is important for any healthcare application. Okay, and then it says the tool provides general health information only. It's not substitute for professional medical advice, diagnosis, or treatment. Okay, so and then we'll start off with the chatbot asking our user. Okay, hello test user, I'm here to help access your symptoms and guide you to the right care. What symptoms are you experiencing today? Right? Okay, so let me now walk you guys through some test scenarios. Okay, so for our first test, I like to demonstrate an emergency scenario. So maybe let's type in something like having chest pain and difficulty breathing. We'll see what happens. Okay, I have severe chest pain and difficulty breathing. Okay. Right, so our system immediately flagged this as an emergency. Urgency level is emergency, okay? And told the user to call 911 or go to the nearest emergency room, okay? Notice it says CTAS level 2, okay? And shows the match symptom, difficulty breathing. So this is layer 2 in action. The CTAS safety rules caught the life-threatening pattern. So like I showed you in the architecture earlier, so when it goes to layer 2, the ML layer model, layer 3 was never involved. This is exactly the design intent. Emergencies are handled deterministically with zero reliance on statistical predictions. So right now, let us go to the next test scenario. So I'll be typing uh, something like I've had a high fever, abdominal pain, and vomiting for 3 days. Okay. So this time I'm actually describing non-emergency symptoms, high fever with abdominal pain and vomiting. So notice our model is taking a while to load. So I'm pretty sure this has been passed on to the ML layer. So when passed on to ML layer, if our model is not able to make a confident prediction, you go back to OpenAI, right? So that's why it's taking some time. Okay, so let's just give it a while to load. All right. So the result shows urgency level, urgent in orange. Okay. Okay, you can see it actually says our model couldn't make a confident prediction. Okay, so this means that the ML confidence was below 70%. So the system fell back to the OpenAI for guidance. So OpenAI correctly accessed this as urgent, right? And recommended seeking medical care. Okay, there's a HealthLink BC number here called 811. Okay, and we have the facility finder page developed in the subsequent sprints. So notice we also have a urgency level guide. Okay, at the end of every conversation. So urgency level guide, you can see we have 4 levels: emergency red, or call 911, urgent in orange, routine in yellow, which is walk-in doctor, and self-care, which is just basically taking care of yourself at home. And notice there's a safe assessment button. When we click on this safe assessment button, what will happen is that this record will be saved into our SQLite database. Let me just quickly pull up database to show you guys. Okay, it's my database loading. Okay, just quickly pull it up. So yeah, we are a test user. So yeah, it's shown here. I've had high fever, abdominal pain, and vomiting. Okay, so yeah, okay, so the this assessment is actually safe. So notice earlier on in the emergency case, this wasn't safe because, this wasn't, this was automatically saved into our SQLite database. So we didn't have a save button because for emergency cases, obviously, yeah, it's life-threatening. It's not possible to actually maybe not possible to get the user to click on the button itself. So for only emergency cases, we won't have the button, so the record will be automatically saved into our database. And notice there's a clear chat button. We can actually clear chat, okay, to make it cleaner. Yep, so let us go to the next scenario. So for the next test scenario, it's a bit long, so maybe let me just copy and paste in. Okay, I have burning mutretion, bladder discomfort, foul smell of urine, and continuous feel of urine. So notice this is I would say this is an important test because this is where the machine layer model actually fires. Okay, so looking at the result carefully, it says predicted conditioned urinary tract infection at 100% confidence. So this is the ML model making the classification, not the open API. The model was trained on 41 disease categories, and these symptoms match the UTI pattern perfectly. So the urgency is routine, okay, which is see a doctor. So contrast this with the previous scenario where confidence was low, the system actually fell back to OpenAI. So that's the 70% threshold in action. Okay, the same architecture but 2 different paths depending on how confident the model is. Okay, so let me save this assessment, right? So it's saved. Okay, and then we'll go back to the next test scenario. Okay, let me just type in. I have runny nose and mouth cough. Okay, so notice the result is self-care and green again. Our model wasn't confident enough with only 2 symptoms, so it fell back to OpenAI, which correctly classified this as a likely common cold. Okay, yeah, it says here, you likely have a common cold, stay hydrated, rest, and consider over-the-counter medications for symptom relief. Use saline nasal sprays for a runny nose and cough drops for throat irritation. Monitor your symptoms. If they worsen, consult a doctor. Okay, right, okay, save assessment. Okay, and the last scenario which I like to show you guys is an edge case. So what will happen if users input something which is not related to health symptoms? Let's say users say something like, "Hi there, how is the weather in Vancouver today?" Right? Oh, right. So our system responds with no symptoms could be identified from the description. Please try again with more detail. So this is exactly layer 1 doing its job. OpenAI correctly determined that there are no medical symptoms in the input, and the pipeline stopped before reaching layer 2. the CTAS layer or layer 3, the ML layer. The system handles this off-topic input gracefully without crashing or giving a nonsensical result, right? So I've finished the demonstration of all the test scenarios, and I want to talk about the current limitations with the system symptoms assessment chatbot. So I want to be transparent. So the first limitation is that our chatbot is currently operating as a singleton assessment. So notice when the user describes all symptoms in one message and the system responds, okay, but ideally, we want the chatbot to ask follow-up questions like how long have you had these symptoms on a scale of 1 to 10, how severe is the pain before giving a final assessment. This multi-turn conversational flow, I've planned it for sprint 3. Okay, so the other limitation, you might have noticed that some of our test scenarios fell back to OpenAI rather than using the ML model. This is because our model was trained on data with 7 or more symptoms per disease, but in real usage, people typically only mention 2 or 3 symptoms. So the model correctly says, I'm not confident enough and differs to OpenAI, which is the safe behavior which I designed. Okay, so the multi-turn conversation I just mentioned should be able to help address this because asking up follow-up questions means gathering more symptoms, which means higher ML confidence. So for the today I have demonstrated the most to me the most interesting feature symptom assessment chatbot. But in sprint 3 we are planning for features which include like the multi-turn conversational chatbot which I just mentioned earlier with follow-up questions. We also have the personal health dashboard, okay, with plotly visualizations, and then in sprint 4 we'll be developing the rest of the features: facility finder, health education library, system analytics dashboards. And in the last sprint, we'll wrap up by having the final integration testing, performance optimization, and project documentation. Okay, so now I'd like to show you the technology behind this application by walking you guys through the actual code. Okay, so just let me pull up my VS Code. Maybe let's just stop it first. Okay. Okay, I stop it. Okay, so before I walk you guys through the code, maybe let me just quickly show how the application starts. So unlike traditional web apps that have a separate front end and back end behavior, so Streamlit handles this both in a single process. Okay, so from the terminal, I will navigate to source directory. I will run one command. So now we are already in the source directory. So I'll just type in Streamlit. Actually, I already have the command. So okay, let's run this command. Okay, that's it. So you can see here, one command will help us start the entire application. So Streamlit serves as both the UI and the backend logic on localhost port 8501. So this is one of the advantages of choosing Streamlit for this project. Okay, the simplicity of deployment. So I will just click on the URL. Okay, so now we are back. Okay, so yeah, yep. Okay, and I also like you to give you a quick overview of the tech stack we are using here before I look at the individual files. Just let me pull up the midterm report. Okay. Okay, right here. Okay, so we can see here we are our web framework. We are using Streamlit Python, AI NLP. We are using Open AI API, GPT-4 Mini, and machine learning. We are using scikit-learn, random forest. Safety rules, we have the custom Python, which is CTAS. Database, we have SQLite. Security, we're using bcrypt, and version control GitHub. So I just want to summarize here. The key thing to understand is that this is a Python only stack. So everything, the UI, the AI integration, the ML model, the database, everything is written in Python. So Streamlit eliminates the need for a separate front-end framework like React or Vue.js, which means I can focus on the logic rather than on HTML, CSS, and JavaScript. Okay, so now I'd like to show you guys how the project is organized. Okay, so let me just walk you guys through the folder structure. Maybe just let me collapse everything first. Okay. The main entry point is right here. Okay, app.py. So this is what Streamlit runs. It handles the login and registration screens. So app.py is both the starting point and the authentication front end, right? Okay, so our front end, if you're wondering where we store our front end code, all our front end code is in actually the pages folder, source, okay, the pages folder, yeah, over here. So this is where our front end code is actually stored. Okay, the pages folder basically contains the UI for each feature. So in Streamlit, every Python file in this folder automatically becomes a page in the sidebar. So we have shown you earlier. So home.py basically is the home page, symptom assessment is the chatbot interface, dashboard is the personal dashboard, and so on. So these files handle what the user sees, the layouts, the forms, buttons, and displaying results. And then where's my backend? My backend is in my components folder over here. Okay. Yep. So all the logic that runs behind the scenes is actually in the components folder. This is where the real work happens. So let me just briefly map each file to what it does. Okay. So yeah, we have the open utils.py file. So this is earlier I mentioned layer 1. This calls the OpenAI API to extract symptoms from natural language. And then we have the rules.py. Yep. This is layer 2, the CTAS safety rules that catch emergencies. And then we have the train model.py. This is layer 3, okay, the script that trains the random forest ML model. And then we have the chatbot.py. Okay, this is basically just an orchestrator that connects all the 3 layers in sequence. And then we have the database.py, where our SQL-like operations are, save users, save assessment, retrieve data, is all here. And then we have org.py. So this is the bicrypt password hashing, login verification, as well as session management. Okay, so when I show you guys the chatbot demo earlier, here's exactly what happened behind the scenes. The symptom assessment page in the pages folder captured my input, send it to the chatbot.py in components, which called the OpenAI utils.py, and then the rules.py, then the ML model, and return the result back to our page for display. So notice here that the front end and back end talk through symptom Python function calls. There are no API endpoints, no HTTP requests because the Streamlit keeps everything in one process. Okay, so I also like to show you guys the other folders. So the models folder over here, okay, yeah, over here, it stores the train ML model as a model.pkl, yeah, and it's metadata. The data folder also has our Kaggle training data set. Yeah, over here, and the urgency mappings I created. And the notebooks folder has the over here, notebooks folder. Yeah, over here, yeah, it has the Jupyter notebooks I use for data exploration model training. So if you like to understand more on how we train our model for the ML classifier layer, you can look at my Jupyter notebooks. Yeah. So To summarize on this section, I would like to highlight a key design principle. So in the traditional web app, right, basically we have a front end that makes API calls to a backend server. But because my project uses Streamlit, it collapses that into one stack by still maintain a clean separation of concerns. So the pages folder will handle the presentation, what user sees. Components folder will handle the logic, what the system does. And the models and data folder will handle the state, what the system knows. So the separation means I can change the UI without touching the ML model or retrain a model without touching the chatbot interface. Yeah, so I believe this is good software engineering practices regardless of the framework. Okay, so now I want to transition to some of the code which I like to show you guys. Now that you seen what the application does from the user's perspective and you have a mental map of how the code base is structured, I want to quickly touch on the two most technically interesting files. Okay, the rules.py is our components folder. Okay, rules.py and which handles the CTAS safety layer, and the other file I like to show is the train_model.py. This will train the machine learning model. Okay, so let's quickly just give you guys a very quick summary, because if we're really going to deep dive in the code, I think I have to do it in another session. Okay, so basically this is the rules.py, the CTAS safety layer. Okay, so it will contain 4 emergency patterns I defined based on the Canadian Trust Guidelines. Each pattern has keywords, as you can see here. Yeah, and the match type, for example, the heart attack, right? It requires both chest pain and shortness of breath to trigger. So the function will loop through all the rules, and if any matches, it immediately returns an emergency result. So the ML model will never run. So if nothing matches, if nothing matches, then it will passes the symptoms to the ML layer. So the key point is that this layer is deterministic, no probability, no randomness. Same input will always give the same output. Okay, and the next file I would like to talk about is the train_model.py. So this is the ML layer. Okay, so basically this layer takes the Kaggle data set of 41 diseases with 131 symptoms, unique symptoms. It converts them into multi hot encoding. Okay, it's over here. Let me quickly show you guys. Yeah, multi-hot encoding. Yeah, multi-hot encoding, which is essentially a binary matrix of all symptoms which are present, then trains a random forest classifier with 100 decision trees. Okay, so if you look, if you have a chance, take a look at my notebook, you'll notice that the model achieved 100% accuracy on the test set. And I want to be upfront, that's because the data set we're using from Kaggle is clean and perfectly balanced, not because our model is perfect or there's overfitting. Okay, that's exactly why I built the 70% confidence threshold you saw in the demo. When the model isn't confident, it falls back to OpenAI rather than guessing. The train model we have saved under the models folder. Yeah, okay. Save as model underscore, model.pkl, and it's loaded at runtime. Okay, so yeah, I've talked quite a bit today. I just want to summarize. So to summarize, if you can take away something from this presentation, today we have 3 layers in our design architecture. Layer 1, understand your symptoms through OpenAI. Layer 2 protects you from emergencies through CTAS rules. And layer 3 classifies everything else with machine learning with a safety net for uncertainty. The remaining sprints, like I mentioned earlier, will add the conversational multi-turn chatbot, personal dashboards, facility finder, and health education library. Okay, so thank you very much for watching.